Howdy everyone, Ryan Schul with Straight Data Science. So today I want to introduce the topic of support vector machines. I'm going to try to do it very crisp, very clean, very clear, and just break this down and tell you what it's all about and give you a good practical case study here where we can apply this kind of methodology. Okay, so SVM is the abbreviation for a support vector machine. This is basically a supervised machine learning technique where we use classification or regression. Okay, there's two types of machine learning methodologies: classification and regression. I have several videos on my channel about both. I get into depth about both. I'm not going to do it here because that would be a little bit redundant, and I want to stay on point. But basically, this works by finding the hyperplane, or the best way to separate different data points in a highly complex set of data, or a high rich feature set of data. Features are columns, or they are um, indicators in the data set. So when it gets really complicated, sometimes we need to just break this down into fundamental components and see how we can separate these data points so we can understand the variance of the data and the message and what the data is trying to communicate to us. Okay, so basically it's very effective for high dimensional data spaces where you have lots and lots and lots of columns, and we can reduce it down to just a few columns and see what really is impacting the target variable. Remember, with machine learning, we always have a bunch of independent variables, and we want to see how that has an impact, some type of statistical impact on the target variable. The target is what we're trying to predict. So I set up a hypothetical but very realistic set of data here. And where's my mouse? Oh, there we go. Oh, okay, so let me refresh the cell here. So we're looking at credit scores, debt to income ratio, loan amount, interest rate, employment length, delinquency rate, revolving balance, annual income, and we are calculating the default probability. So this is a derived column, right? This is called feature engineering, where I'm applying a small mathematical operation to all the other columns that we had that we created originally, from credit score up to annual income. So I want to take all of this and see what kind of impact that has on the probability of default of this loan, and then come up with a flag. Could this loan possibly be defaulted, yes or no? That's what we're trying to do here. So I have my data. I'm going to feed it into my model right here. So the independent features are the x variable, right? We take everything except for the y, and default probability, and just dump everything from credit score over to annual income into the x variable, and we're trying to predict the default, right? So I want to see which of these features have an impact, a statistical impact on the default of a loan, right? So we can look at the precision, recall F1 score, and support. So the higher the better. I want these numbers to be pretty high. 0.98, that's fine. That's excellent. 1.0, 0.99, and 293, that is fine. This is a little bit lower F1 score, and this is a little bit lower. So the reason for this is most loans don't default, right? So when you have zero is like false, right? 0 is nothing. 1 is the default, and that could be true. This could be yes or no. These are always binary. So it's always going to have, the model is always able to make good predictions into the future based on what it's seen in the past, the data that we dumped in, right? All the data comes from here. It can look at all this data, understand what triggers a default, and be able to predict that, or what predicts a not default, and be able to predict that. But we don't have too many defaults. Most people are paying off their loans on time. Most people are credit worthy, or what's the word? Not transactional, solvent. Okay, most people are solvent, but sometimes people can't pay for a variety of reasons, right? So we do have some defaults, but that's the exception. That's not the rule, right? So sometimes the model can't learn too well because it just doesn't have too many instances of these defaults. And there's ways to handle that. And you can oversample from the undersampled, or from the underrepresented population. You can undersample from the over represented part of the population. This video is not about that. I have a couple other videos that describe how to do that. So I'm just going to leave it alone. The model's learning pretty well. It's not perfect, but it's doing a pretty good job of learning, and then we're able to make predictions. So let me refresh this so we have so we know how many vectors we have. So we have a total of 24 vectors. So again, we have a big feature space with a lot of columns here, and the support vectors are actually 24, and we're trying to understand which vectors here are going to have an impact on the target variable. Again, this is the default of a loan. We're trying to predict the probability of a default or understand which loans can default. So if we see a default over here, okay, so if we have all zeros, and that's totally fine. Most of these are going to be zero. It's not in default. But if we have one default, if we have a 1 in this column, we can go back over here and look at the credit score and the debt to income and the loan amount, interest rate, employment length of time, delinquency and revolving balance and annual income, and see like what kind of matches up and what creates the default. Which features over here, if they're all assimilated together, is probably going to trigger default. And we collect this information from our client. We collect all of these potential data points or data points. We collect all of these to do this potential analysis. And if it comes out just the wrong way, we're not going to issue the loan because historically what has caused a default, right? So that's the whole point here. And SVM, a support vector machine, is going to help us make that determination, right? So we're looking at the boundaries of high dimensional data. Remember, lots of columns, right? High dimensional data has lots of columns. It's very complex because there's so much stuff going on here. It's hard for a human to comprehend that and to assimilate that and to distill that, right? So we need PCA to reduce the dimensionality. So we're actually going to lean on another methodology called principal component analysis to see how these features look in a two-dimensional space, okay? So the SVM, the support vector machine that we're visualizing, is not, you can't really visualize it. It's just too complex. But we can map these to a PCA method and then visualize it in 2D space. So that's what this code does right here. And you don't have to worry about like learning all the code and understanding all the nuances of everything. I put this together, tested it, and debugged it and everything. So this is fine. But my hope is that you can copy and paste this into your own Jupyter notebook and run it and learn from that. That's the goal here, right? So I'm trying to drop some knowledge and teach you a lesson. So I can't get into like all the details of every single thing. Otherwise, these videos would drag on for hours on end. But the point is just to show you like the nuts and bolts of data science and introduce you to this and get you acquainted with these concepts. That's my goal here, right? So I can't go through every single line of code. It would take hours to do that. But I just try to put together the code, I test it, and debug any issues, and then I will save it and I'll share this as this HTML file with you so you can run the code on your own machine and learn from it. So you can see 1 is true, 1 is red, and 0 is false or no default, right? So we do have a few defaults in here, okay, and they are represented by the red dots over here. But by and large, most of these loans are not going into default. You'll always have a few. You'll always have a handful that just don't work out for whatever reason. But for the most part, none of these are in default, right? So these loans are fine, okay? And we can go down here and map back the support vectors to the original features so we can understand which loans or which features in the loan data set here that we're looking at are the most critical to the SVM decision, support vector machine decision that we're making, and we want to see what is going to have an influence or move the needle or have a statistical impact on predicting the target variable. Again, the target is the default. Is the loan going to go into default or is it not going to into default? And it's based on all of these features down here. So let me refresh this, okay, and refresh the chart as well, just so we can see visually what's going on here. So the diagonals are removed on this chart. We don't need to see that because everything is just correlated with itself, right? We'll have nothing really to plot there. But each cell in the matrix shows a scatter plot comparing two features from the support vectors, okay? And the colors are either blue or yellow. So yellow is default and blue is not default, right? So you can see that over here. So I always say a picture is worth 1,000 words. I think this is a nice visual here. It shows us the defaults and the non-defaults, and then each feature relative to all the other features. Okay, so let's look at again all the independent variables. These are the x variables, and what has the most predictive influence on the y variable. We're going to use log regression for that. So let me hit Control Enter. And we can see right here using log regression. And again, there's a few different ways to do this analysis, right? We can use a few different models. We don't have to just rely on one. I have another video on my channel about how to pick the best model and how to automatically pick the best pick the best model too. So I have a video on that. You can check that out. That's very interesting. So we'll run a couple different models just because we want to see which model is going to produce which outcome, or what the result will be, what the report will look like, because you don't know in advance. It's impossible to say, well, this is going to be the best model for this data set. You have to try a few different models and see what the outcome is, and then pick the best performing model. That's the only way to do it. You can't tell in advance which one is going to perform well. And the data can actually change over time. So one model that you have been using for a couple of years, this is called model drift. I have another video on that. Maybe that one was performing well for years, and now maybe it's not doing so well, and you have to train and test a different model, right? That's model drift because the data can change over time too. So the takeaway here, we're looking at the different features and the coefficient. The higher, the better in terms of impacting the target variable, or the more influence it has on the target variable, right? So the higher the number, the more influence on the target variable, which is the probability of default. So using this model, the interest rates that are being paid on the loan can cause default the majority of the time, and the revolving balance for the client that's receiving the loan is very tiny. So that's money coming into the account and coming and going out of the account that has almost no impact whatsoever. It's really interest rate. So that totally makes sense if you think about it. If you have to charge a huge interest rate on the loan, there's a higher probability that the loan will default. If the interest rate is lower, then there's a much lower probability of default. Debt to income ratio, if there's a lot of debt, there's going to be a higher probability of default. And if you're employed at the same job longer, let's say 2 to 5 years, that is going to tell me and tell the model and tell everybody else that this person probably won't default on the loan. If you've only been at your job for 2 months, then I can't tell. Like, I don't know if you're going to pay off that loan or not. I just can't tell. But longevity and consistency and persistency definitely has an impact on the target variable. So we can do another type of analysis. This is called feature importance. We're using random forest classifier. I like this a lot. I use random forest classifiers and XGBoost classifiers a lot. So here, this model is slightly different. We're looking at the features and then the importance of predicting the target variable. There's the matrix there. We won't spend too much time on that. We'll jump down here to a chart that shows us visually. Okay, the loan amount is the biggest and the employment length is the least. So employment length is the least and loan amount is the biggest. And it's interesting here because over here, employment length was number 3. Okay, but that did have like a less impact, I guess. But that's fine. Oh, you know what? These aren't even sorted in order. I just noticed that right now. So sorry about that. But definitely the interest rate has the biggest impact. Revolving balance has probably the least impact. A couple of these are negative. I did not sort this. Maybe I can swing back and do that before I actually post the video. I can make a little update here because it would just make it a little bit easier to read. But again, we're using a different model. This is a log regression model. This is a random forest classifier model. So almost guaranteed they're going to produce different results, right? You have to run a few different models and see what the outcome is. So in this one, we can see the loan amount about 24%, 24% of the time. Yeah, 24% of the time, this is going to have an impact on the target variable. Again, the target is the default, whether you're going to go into default on that loan, whether it's a car, house, for a business, doesn't matter. The loan amount is going to determine the probability of default 24% of the time. The debt to income ratio has an impact. That makes sense. The more debt you have and the lower income you have, it's probably going to cause a default rate, interest rate on the loan. We saw that before from the log regression. Annual income plays a part. And here, employment length actually only has 4% influence on that target variable, whereas loan amount has a 24% impact on the target variable, right? So you add these together, it's going to be 100% or pretty close to 100. Maybe there's a rounding issue or something. So that's it, right? So in this case, like if I was a loan agent, what's it called? Mortgage or mortgage broker, maybe, I think that's the term. So if I was a mortgage broker, I would be focusing on the loan amount, the debt to income ratio for the borrower, and the interest rate on the loan, and probably the annual income of the borrower too, because these are going to determine, for the most part, whether a default will occur or not. Revolving balance doesn't matter too much. Credit score doesn't really matter too much. Delinquency rate on other loans kind of has an impact, but not too much. And employment length really doesn't matter that much. But we still captured the information, and it still does have an impact. But the top three here are loan amount, debt to income, and interest rate. So why are we doing this type of analysis? So for support vector machines, basically, this solves the optimization problem to maximize the margin between the closest points of different classes. These are the support vectors, okay? And this works well in high dimensional data space. Again, high dimensional data space has lots and lots of columns, lots of features. We take all these features and compress it, or collapse it, condense it, whatever you want to call it, into a smaller set of features. So if we have hundreds of features and several of them, most of them don't even matter on playing an influence or an impact on the target variable, we don't need to know about that, right? We're taking a lot of data and distilling that down into um, a smaller amount that is easy to digest and understand and assimilate, right? So we don't want this high dimensional data. We want to condense it into a smaller data set so we can comprehend it easier, okay? So the benefits is just easier processing for the machine, for the algorithm. It doesn't have to learn on data that's irrelevant. It doesn't have to maybe mislearn data, right? Like, you want to keep it relevant, you want to keep it tight and crisp. So you want the features that are going to have the biggest impact on the target variable and feed that into the machine. If you have 120 features and only 5 or 6 really impact the target variable, there's no reason to train the machine on 120. It takes a lot more resources, computational power, time, and the model could actually mislearn and think some of the other features maybe are important, when you know for a fact, after doing this exercise, this SVM exercise, you know for a fact that's not important. Don't even go down that path. Don't even try to misguide the algorithm or mislead the algorithm, right? Just give it what it needs and let it do its work, okay? And this provides decision boundaries, which are hyperplanes that can be visualized in either 2D or 3D space, okay? So that's pretty much it, guys. Hopefully I can break it down for you and help you understand this concept. I think it's pretty interesting, and it is used in the real world. I haven't used this tons and tons of times, but there is a spot for this type of analysis. So hopefully it that makes the point. If you have high dimensional data, you can get down into low dimensional data space, do your analysis, and everything is lovely. Okay, so I'm going to wrap it up here, and I will see you guys in the next video. Thanks. Goodbye.